So next we see about LST, linear strain triangular element. A 6-noded triangular element is known as linear strain triangular element. It has 12 unknown displacement degrees of freedom. The displacement functions the element are quadratic instead of lines as in the CST. So if we compare with the CST, that is constant strain triangular element, in LST have additionally 3 degrees of freedoms. In CST element, the displacements we consider only in the node points. It is U1, V1, U2, V2, U3, V3 at the node point. Whereas we considering the LST element, we have considered each linear strain element. Each linear strain element means in between the two nodes. We consider that point, and mostly we prefer the center point of the element. So totally we triangle have 3 nodes, so we get a degrees of freedom at the node points, that is the CST element. Additionally, we have add displacements, consider displacement at the center point of the link, that is linear strain triangular element. So this is a diagram shown here, we can easily absorb. So determine, these are the sums, some are the sums given here. Structural mechanics applications in 2 dimensions. Elasticity equations are used for solving structural mechanics problem. These equations must be satisfied if an exact solution to a structural mechanics problem is to be obtained. These are 4 basic sets of elastic equations of strain displacement relationship equation, stress strain relationship equations, equilibrium equations, compactability equations. For truss element, a truss element is defined as a deformable two-force member that is subjected to loads in the axial directions. The loads can be tensile or compressive. The only degrees of freedom for one-dimensional truss, that is bar element, is axial, that is horizontal displacement at each node. So assumptions for one-dimensional truss element: prismatic member. The truss element is assumed to have a constant cross section, that is, it is a prismatic member. If a truss structure is stepped, then it must be divided up into sections of constant cross section in order to obtain an exact solution as shown. If a truss structure is tapered, then it can be approximated by using many small truss elements, each having the same cross section at middle of the tapered length. It is approximating. The more sections that are used to approximate the tapered stresses, the more accurate the solutions will be. Weightless member. Weight of the truss is neglected since it is assumed to be much less than the total resultant forces acting under stress. If the weight of the truss is not neglected, then in effects must be represented as vertical forces acting at the nodes. But since stress element is defined as two force members, it cannot be have any vertical forces. Thus the member weight has to be neglected. If the shear stress exists, then a beam element must be used to model the structure. Nodal forces. The one-dimensional truss element forces, that is loads, can only applied the line nodes of the element but not between the nodes. This is considered with Fermi equations which relate nodal forces to nodal displacement through the stiffness matrix. Axially loaded. For one-dimensional truss element, forces, that is loads, can only be applied applied at the centroid of the element cross-sectional area. Buckling effect not considered. A bar element can be subjected to either tensile or compressive forces. Tensile forces have been applied to the bar of any cross-sectional area or member length, and failure is associated with sudden fracture or general yielding. When the comparative forces are applied to a member, it can neither fail due to crushing or buckling. Buckling is present when the member bends and laterally deflects as shown in the diagram. Buckling is not accounted for in formulation of the truss element. Members that don't buckle are classified as short columns, and members that buckles are classified as long column. The structural response of a short column can be predicted with truss elements. To determine if buckling will occur, the reader should refer to a mechanics of material textbook. We will now introduce a simple geometric guidelines to determine if the buckling might occur if the ratio between the member's length and the least dimension of the cross section is equal to less than 10. The member is considered a short column and buckling will not occur. That is, the least cross sectional dimensions m member's length. In the second case, if a bar element is subjected to a compressive force, the element will not predict the buckling response. One should note that the above general rule is a simple guideline. However, in reality, buckling depends not only on the member's length and cross-sectional area but material properties and support conditions.